Hi all, I'm known as Fireflight in the Constellation Network community, and I'm an active member in the Stardust Collective where we focus on pushing educational content and general hypergraph ecosystem growth. Welcome to my Euclid introduction video, where I'll walk you through the Euclid development environment and show you how to set up your local machine for developing metagraphs. To get started, you can go on the quick start page that's available on the Constellation Network documentation pages. I'll include a link in the video description. So without further ado, let's get started. If you are developing on a Windows machine, you'll need to install WSL first before continuing the installation, because the development environment works best in a Unix-based environment. WSL is a Linux kernel that runs inside your Windows environment, so you can easily access Linux while staying in your Windows environment. If you are using a Macintosh or Linux environment, you can skip this part. I'm developing on a Windows machine, so I'll first go through the WSL installation part. You can follow the install instructions that are available through the install WSL link. To install WSL, you can open a new PowerShell terminal in Windows and run the install command. I'll use Ubuntu 22.04 since that is the latest long-term support release of Ubuntu. Once the Ubuntu distro is installed, you'll need to choose a username and password. I'll use tutorial as my username and set a password for that. The terminal will open your Linux session after the installation is complete. I'll try to visualize our setup to make it easier to understand where components are installed. So far, we have installed Ubuntu through WSL in our Windows machine. The next component we need to install is Docker. This is a container runtime that allows you to easily run containerized applications. Starting this point, Mac or Linux user can start following along. The setup is quite straightforward and you can follow the instructions from the Docker documentation page. Choose the appropriate installer for your environment and complete the installation. Once that's set up, you can open the Docker application. You won't see any containers yet, as we are not running any apps yet. The next thing you'll need is a code editor. I would suggest installing VS Code, as it's a free IDE and has a ton of extensions available to help you with your development. Go to the VS Code website and download the installer for your system, which is Windows in my case. The installation is very straightforward. Now we can start with installing the prerequisites. On a Windows system, we will install these inside the Ubuntu WSL environment. On a Macintosh or Linux system, you can install it directly on your system. Let's start with installing Node.js next. There are different ways you can go about it. You can go to the Node.js website and follow the instructions to install it. In our case, we want to install it on Linux, so we can go to the other downloads link. I usually prefer to use a package manager, so you can click through this link and choose the Debian and Ubuntu-based Linux distribution, where you can find the binary distributions link that contains the installation instructions. You can choose the version you want and copy the command. In our case, we want to install Node.js 16, so you'll need to replace the reference to 16 and execute the command in your terminal to install it. However, if you're on a development machine, I would recommend to use the Node version manager instead, because that allows you to easily switch between different Node.js versions, which can come in handy. Go to the GitHub page of NVM and execute the install scripts. You can copy the curl command that executes the installation and paste that in our terminal. Once that's done, we can run this export command to load the NVM profile in our current session, so we don't need to exit our terminal. Now we can use the nvm install command to choose which Node.js version we want to install. In our case, we want to install version 16. Once it's installed, you can use the nvm use 16 command to load that version. To verify it's correctly installed, we can execute the version command. The next thing to install is Cargo. So go to the cargo link and just copy the command and paste this in your terminal. Choose to proceed with the default installation option. And to configure our current shell, you can run the suggested command at the end. Okay, now we can install Scala. We will install this on our Linux environment, so don't choose the Windows installer, but choose Ubuntu instead. If you are on a Mac, you need to follow the Mac OS instructions. Copy the install command and paste it in your terminal, which will start the installation. It detected that we don't have a Java virtual machine installed yet. We want to include this, so confirm that. Choose yes to update the profile and choose yes to add Corsair to your path. Once that's completed, you can check if Scala is installed by entering the version command. As you can see, it's not detecting our installation. You'll need to close the terminal first and open a new session. If we do a Scala version check now, you can see it's correctly installed. We also need to install JQ, so follow the instructions for your system. For Ubuntu, you can install it using apt-get, so copy the command and execute it in your terminal. Before installing RC, you'll need to install the Build Essential package if you are using Ubuntu. You can install this through the apt package manager. Now we can install RC with the provided command. Once that's done, we can install Gitter as well. Alright, once that's done, we have installed all of the prerequisites. We also need to create a new GitHub access token. This is needed to build the tessellation binaries. You can navigate to the GitHub settings page where you can generate a new token. Click the button to generate a new token and use the classic option. We'll use it for Euclid, so I'm adding that as a label, but it doesn't matter what value you enter here. You can set an expiration date if you want. Since we only provide read permissions on packages, it's okay to not expire the token. We will only check the read packages option and then we generate the token. You can see the generated token after you clicked the button. Copy it and store it somewhere safe. You won't be able to view this token again once you leave the page. If you lose it, you can always regenerate a new token. Our machine is now ready to configure Euclid and get started on coding our metagraph. We can install Euclid by cloning the repository into our development environment. In my case, I need to clone the repository in my Ubuntu environment inside Windows. If you use Mac or Linux, you can clone it directly on your system. You can clone the Euclid development environment by copy-pasting this code into your terminal. Once the repository is cloned, you can open the project in Visual Studio Code to continue the configuration. You can open Visual Studio Code by entering the command code, followed by a dot to open it in the current project directory. This way you can easily access the files from Ubuntu in your Windows environment. Let's explore the folder structure of our project first. On top you can see the GitHub folder. This contains a pre-built GitHub workflow that spins up your Metagraph Euclid cluster. You can extend this with custom tests, so every time you push code changes, it runs this pipeline and validates if everything works properly. This is very useful to ensure your code changes don't break anything. Then you have the infra folder, which contains all of the infrastructure related artifacts. There's an Ansible folder that contains a playbook to deploy your metagraph to a remote server. There are different ways you can deploy your metagraph, and it's great to see that the team included a built-in option inside Euclid SDK. I won't cover publishing metagraphs in this video though. Next you have the Docker folder, which contains the Docker configuration to build the images and run it on your local environment. Several images are built in this process, as you can see by the folder structure. The base image is contained in the metagraph base image folder, which is used as the base image for all metagraph images. The folder names are clear enough to determine what images are being built. You have the global L0 image that is used to run one global L0 node. You have the hybrid metagraph L0 genesis and validator node images. Then there is the metagraph L1 currency node image and the metagraph L1 data node images. Finally, you also get some monitoring applications to be able to view some generic metrics of your environment. This uses a Prometheus time series database to store the metrics and a Grafana instance to view the data through dashboards. The scripts folder contains the Hydra scripts, which allows you to spin up your local cluster or publish it to a remote server. You generally don't need to modify anything in the infra or the scripts folder. This is being handled by the Euclid SDK. Finally, you have the source folder where your project-related artifacts are stored. There's a global L0 folder that contains a Genesis CSV file. You don't need to worry about this, it's just needed to spin up your global L0 node. Then you have the Metagraph L0 folder, which also contains a Genesis CSV file. This is where you determine the initial balances of wallets for your metagraph currency. You can see there is a placeholder of 3 wallets where each wallet gets 10,000 tokens when your metagraph genesis is started. When deploying your metagraph, it's important to configure this correctly and set the balances to the initial supply to wallets you control. In the P12 files, you can find the private keys that belong to the nodes. For a local development environment, it's okay to store it in here and use the default files, but when deploying your metagraph to a public network, make sure to use your own P12 files. Also be careful where you store these P12 files. You don't want to include this in a public source control repository, as these are your node wallets. Below that you have a project folder, and you can see currently that folder is empty. This will change when we run the Hydra install script, because this is where our project templates will be generated. From there we can start editing our metagraph. Before running the Hydra install command, we'll first need to edit the Euclid.json configuration file. You need to add your GitHub token and set a project name. I'll just use the default name of custom project, but you can change that to whatever makes sense for you. This is also where you can set the tessellation version and the P12 file references. For local development, it's okay to store the passwords in plain text if you use the default P12 files, but don't store your actual key information in here. Sensitive info like this should be stored in a secure vault. Now that everything is set up, we can start by installing the project templates and detach it from the public GitHub repository so you can configure it in your own repository. After running the install command, you will notice it generated a new folder in our project directory. In the root and the project directory, you can find some files that contain your dependency definitions and instructions on how SBT needs to build your project. You generally don't need to modify anything in here. You have the L0 folder that contains your Metagraph L0 application. You can also find an L1 folder which contains your Metagraph L1 currency application and a data L1 folder which contains your Metagraph L1 data application. All these applications inherit the default implementation from the SDK, so it doesn't contain much code yet. You can customize the applications from here. There's also a shared data folder where you can place code or libraries that would be needed across the different application layers. So basically, we should already have a working metagraph that contains a currency with a default implementation. If all you want to do is deploy a token on the hypergraph without any custom reward mechanisms, then you are basically already done. Let's try to run the cluster and see what we have without having written a single piece of code yet. Let's discover which commands are available in Hydra. You can use the Hydra help command for that, which displays the available commands. There's the install command, which we already executed to install the project templates. With the install template command, you can easily install and run one of the sample Metagraph projects that are available on GitHub. There's a build command which builds out your Docker images. This basically wraps your Metagraph application in an image that can be used by a container runtime to host your Metagraph. Then you have several start commands. There's the start Genesis, which starts up your Metagraph from scratch and generates the Genesis snapshot when the application is starting. And there's a start rollback command that starts the containers from the last persisted snapshot and maintains your history. The stop command stops your containers while retaining the data. The destroy command will delete your containers. And the purge command deletes the containers along with the container images. There's also a status command to see the current status of your containers. You can also use the Docker desktop interface to view this as well. Next, you have the remote command to configure and deploy your Metagraph to a remote server. And finally, you have the update command, which updates your Euclid project to the latest version. Now that we have familiarized ourselves with Hydra, let's start building out the images. Copy the Hydra build command and paste it in your terminal. This will take some time, so it's the perfect time for a coffee break. Once that's done, the images should be built now and you should see them in your Docker instance. You'll notice they're currently not in use yet, so let's try running the application locally. Let's spin up our Metagraph by running the start Genesis command. This will create some containers inside our Docker environment. So if we go to Docker, we should see the containers being created. There's a certain order in which the containers need to be brought online. It first spins up the global L0 node, and once that's online, it'll spin up the Metagraph L0 nodes, and finally it'll spin up the Metagraph L1 nodes. Once all containers are running, it will display a list of URLs. Every layer is hosted on a unique URL that you can use to interact with your cluster. It also generated a Grafana URL that you can access in your browser, where you can see some metrics on your cluster. Let's try browsing to this. The default username is admin and the password is also admin. You'll need to create a better password next. For local development it doesn't matter much, but if you deploy this to a remote server, make sure it's a secure password. In Grafana you can find two dashboards, one for the global hypergraph and one for your metagraph. These contain some general metrics like how many nodes are running, the current ordinal height, consensus duration. Feel free to explore this yourself. Now that our cluster is running locally, let's try to send a transaction to verify everything works. The documentation page includes instructions on how to do this. So let's install the tools for this and try sending a transaction. To install the SDK developer dashboard, we need to clone the repository into our development environment. Let's open a new Ubuntu session for that and run the command. Once that's done, we can run the npm install command to install all the dependencies. To install yarn, you can execute the command npm install-g yarn. After that, we can run the application by running the npm run dev command or the yarn command if you prefer that. Now that the dashboard web app is running, you should be able to browse to that URL on your machine, which should display the SDK dashboard. This is a basic network explorer where you can find an overview of your snapshots and transactions that are happening inside your cluster. On the left side, you can find the global L0 snapshots and supply metrics. On the right side, you can find your Metagraph currency snapshots and supply metrics. In our case, we have a total supply of 30,000 tokens, which is what we defined in our Genesis CSV file. At the bottom, you can see the transactions for L0 and your metagraph, which is currently empty. Let's change that and try sending a transaction. To send a transaction, you can use a DAG4.js script to interact with the network. There are also libraries available on the Stardust GitHub to integrate with Stargazer wallet. For now, let's just copy the example command and use that to transfer some tokens from one wallet to another on our local cluster. I'll open a separate Ubuntu session for this and run the command. Okay, it looks like this worked. Let's go back to the dashboard and see if this transaction is visible. You can see our transaction in the Explorer, where we sent 99 tokens from one wallet to another. This is also correctly reflected in the wallet balances overview, so it looks like everything is working as expected. Let's try customizing the reward logic of our metagraph. We'll try a simple reward mechanism that mints rewards to a predefined set of addresses whenever a snapshot occurs. We can add this in our L0 metagraph logic. I'll first add some imports for the dependencies that we'll use within our function. Next, I'm adding a new object called rewards mint for predefined addresses, which we'll use to create reward transactions for a set of predefined addresses. This object is a factory for our function that generates the reward transactions. We'll create a make method that returns a new instance of rewards. We can use the distribute trait to accomplish the reward distribution. Let's distribute 5.5 tokens to each wallet. The unit you define here is the smallest division possible for a token, so we aren't using decimals when working with the amounts in our metagraph. Given that a token can be divided up to 8 decimal places, the smallest division represents 100 millionth of a token. So 5.5 tokens would be defined as 550 million in our code. Next, we'll define which addresses receives the rewards. I'm defining 2 wallet addresses here. We need to cast our list of strings to a list of address types. And finally, we'll create a sorted set of reward transactions for those addresses and return that object. Now we have created a function that executes our rewards logic. The final thing we need to do is override the default rewards implementation with our custom function. This can be done by overriding the rewards definition in our main object. I'll add a link to my code in the video description so you can also follow along with this. Now that the code is updated, we need to rebuild our images. So I'm running the Hydra build command again. I'm adding the no cache flag to force a complete rebuild of my images. Once that's completed, you can scroll up to verify that no errors occurred while building the images. This looks good, so let's run our cluster again using the start Genesis command. Once our cluster is up and running, we can go to our Network Explorer and see what happens. We can see the Genesis snapshot of our metagraph occurred and the initial balances are set to 10k tokens for the 3 wallets we defined in our Genesis CSV. We should see an increase of the balances for the 2 wallets that we defined in our custom reward function. Each wallet should increase with 5.5 tokens with every snapshot that occurs. You can see a new snapshot has occurred and this caused an update in our wallet balances. When looking at the snapshot details, we can see the rewards array includes our 2 wallets with the correctly distributed reward amount. So it looks like everything is working as expected. Now that you made it this far, you can start exploring the capabilities and start playing around with the existing Metagraph examples. The Door Metagraph is also open source, so you can also check that one out. If you want to run an example on your development machine, you can get started quickly using the Euclid install template command. Write down the name of the example you want to run locally and in your terminal execute the command hydra install template followed by the name of the example metagraph. Let's try this with the water and energy usage metagraph. Once the template is installed, we can open our code editor and you'll see the project already contains the code to run this metagraph. This metagraph also makes use of the data API, which is something worth exploring as well. You can check out the documentation pages and this code example to learn more about this. I hope you liked this fast-paced walkthrough of Euclid and hope it helps with your metagraph development. Let me know if you have any feedback on this video or if you'd like to see more content like this. Thank you.